Hey guys, so the first question that students have whenever they start learning about optimization is, I wonder if there's a process to tackle each one of these exercises, given that they're very unique in their own way. Sometimes we're finding the largest area, other times we're finding the minimum surface area, other times we're talking about cost of something. And the answer for that is yes, there's a process that you can go through to guarantee that you check all the boxes and that independently of which exercise you have in front of you, you're able to complete it, to finish it successfully. We're going to talk about that today. We're going to go through that process. And it wouldn't make sense to go through that process without an exercise. So we're going to do an exercise. We're going to solve an exercise at the same time. Now, let me warn you, the exercise is not the hardest one you're going to find out there, but the purpose of this video is not to solve hard optimization problems. It is to go through the process and to guarantee that you've learned the ropes. So let's get to it. The exercise we're going to solve is the following. Find the largest rectangular area one can fence with 4,000 meters of wire, given that one of these sides doesn't need any fencing. Now, there are two things to mention here. Number one, this exercise is not IB style, but the purpose of this video is not to solve IB style exercises. It is to get to know the process correctly so we can apply it to IB style exercises. And number two, I've mentioned here that one of the sides does not need any fencing because, well, if you were to fence all four sides, the answer would be a square, right? Which is not very interesting. So this is a way to make the answer a little bit more interesting. So what's step number one in this process? The first step is to understand the problem, which means answering questions such as, what was given? What do we need to optimize for? And also, is there any restriction? And all of these questions, of course, can be answered right now. So what was given? We were given the amount of fence or the amount of wire that we have. We were given also this piece of information. So one of the sides does not need to be fenced. And what we need to optimize for is for area. We need to find the largest possible area, which means maximize the area. And what does it mean to have a restriction? Well, we're always going to have a finite amount of something. And in this case, the restriction is the length of the wire, which is 4,000 meters, which is a lot of wire. Step number two. And this is a step that you're probably most likely not going to need to worry about for IB style questions because usually 99% of the time they give it to you, which is a sketch. Sketching goes a long way when understanding the problem. So here's our rectangle and our wall. Now, number three is to attribute variables to the given quantities and also to what you're trying to find. So for example, this is a problem that involves the area. So A will be used for the rectangle's area. Also, given that we're talking about a rectangle, we're gonna name the sides X and Y, for example. So let this be X and let this be Y. And there's no need to get fancy here. If you're talking about areas, just use uppercase A. If it's volume, just use uppercase V, and so on and so forth. Step number four, if you have a restriction, find its equation. So what restriction do we have? Well, we only have 4,000 meters, which is a lot actually, of wire. Therefore, whatever we place over here and over here and over here has to add up to 4,000, and there's our equation. So x plus y plus x has to be equal to 4,000. Number five, and this is where things get a little bit more interesting. You're going to define the function to be optimized. And in this case, we're trying to optimize the area. What is the area of a rectangle? Well, in this case, it's just x times y. Now, we have a problem over here. We're defining a model or a function in terms of two variables, and that's where the restriction comes into play. You're going to write it in terms of one variable only. And how do we do that? Using the restriction. We are going to rewrite y in terms of x over here and place it in our function area. which gives us the area in terms of one variable only. In this case, we have the area equal to 4000x minus 2x squared. Okay, so sit tight, we're halfway there. Step number 6, find the critical point of the function which is being optimized. And what's a critical point? The critical point will be the possible candidates for maxes and or mins. The definition is the following. A critical point or a critical number is a number which is represented by C in this little box, which belongs to the domain of f such that either the derivative is equal to 0 or it doesn't exist. Now, for optimization problems, you're going to be finding the points where the derivative is equal to 0, given that we don't care for these applications about numbers that don't belong to the domain of the function. So in a nutshell, we're calculating the derivative and making it equal to 0 so we can find these maxes and mins. For this example, finding the derivative is of course quite easy. We just need to apply the power rule. So we have 4000 minus 4x, and we're going to make this equal to 0. So 4x equals 4000, which means that x is 1000 meters. So this is our critical point. Now the question is, does this give us a max or a min? In order to establish whether this gives us a max or a min, we need to run one out of two tests. You can choose the one that you prefer if, of course, the exercise didn't decide that for you, because sometimes you have in the description of the exercise something like use the first derivative test or the second derivative test. So I kind of already answered the question, but the way to establish or to define whether you have a max or a min is to either use the first or the second derivative test. And something else that's important to mention here is 1000 is not the largest area. 1000 is the x value, which when selected will give you the largest area, which implies in this case that given that y is 4000 minus 2x, y will be 2000 meters, which means that this is 1000 and this is 2000. So when you consider this length right here as well, we have in total 4000 meters. So step number 7 is to use the first or second derivative test to prove you found a max or a min. Depending on the problem, in this case, we're finding a max, so we gotta prove that we actually found a max. Now, how can we use these first and second derivative tests? How do they work? For the first derivative test, suppose that you find a critical point, which we're labeling C right here, and in a continuous function f, okay, that's fine. If f prime, which means the derivative, changes from positive to negative at C, meaning that before C it is positive and after C it is negative, then f has a local maximum at C, at the critical point C. Now if it changes from negative to positive, then f has a local minimum at C. Now how do we apply that to this context? Let's apply it before we move to the second derivative test. We're going to check that we actually got a max using both tests. You're just going to do one of them in your question, in your exam, in your exercise, but we're going to do with both of them today. Knowing that the critical point found is x equals 1000 and the derivative is given by 4000 minus 4x, we are going to plug in to test what the sign of f prime is for an x value which is less than 1000 and then greater than 1000. So we can use, for example, 0 and 2000. And what is f prime of 0? Well, that's just 4000 minus 4 times 0, which is, of course, 4000. And what's important here is to know that this is positive. It doesn't really matter if it's 4000 or 12,000. The only thing that matters is the sign, and this is a positive sign. It's a positive number. And what is f prime of 2000? That is 4000 minus 8000, which is negative, meaning that before or for numbers less than 1000, the derivative is positive, and for numbers which are greater than 1000, the derivative is negative, which means, by the way, that the function is increasing and then decreasing. Therefore, at x equals 1000, we have a max. If it changes from positive to negative, we have a local max. All right, so how do we use the second derivative test, which for this application is actually better because finding the second derivative is quite easy. Suppose you have a critical point, which is c, and that the second derivative at that point, at that precise point, is greater than 0. Then f has a local minimum at that point, at the critical point. If you have a critical point and at that point the second derivative is less than 0, which means it's concave down, we have a local maximum at c. Now, as you can see, the first thing we need to find is the second derivative, which in this case is just -4, the derivative of the derivative. And it is a constant value, so it's not really a function of x. It doesn't matter which x value we're talking about, the second derivative is always going to be a negative number, -4 in this case. Given that the second derivative is less than 0, then at x equals 1000, we have a local maximum. Now, do know that most often than not, the second derivative for different applications, different types of exercises, it will be a function of x. So you need to plug in the critical point in it to find or define or determine whether it is positive or negative, to then conclude it is a minimum or maximum respectively. And you thought this was the last part of this algorithm, this workflow, but it is not. The last one is number 8, which is to answer the exercise. What do I mean by answer the exercise? Well, in this case, we're asked to find the largest rectangular area. We found x and y, but we didn't find the area. Given that the area of a rectangle is base times height, the answer is 2000 times 1000. Let me write this down, which is 2 million square meters. And there we go. This is the answer for the exercise. With this recipe, with these 8 steps, you should be fine in answering any type of optimization question.